Hello, gentlemen. How's it going? Oh man. Uh, so I wanted to do a series on how an antique radio works in really good detail from start to finish. So I'm gonna set about doing that today, and I'm gonna try to do it in an order that makes sense. And I think starting with the power supply probably makes the most sense because it's the if you don't have a power supply, you don't have a radio. So pretty important stuff here, and let's yeah. So, just one quick side note before I get started. It's been a very rough month over here. I live in Western North Carolina, and we were hit extremely hard with Helene. I live in a floodplain, so we had almost the water was almost up to my head in my house. So we didn't lose as a lot. We didn't lose as much as some people did. So, we count ourselves as fortunate. We were actually closing 5 days after Helene hit on our house. So, I mean, it's depending on how you look at it, it's either really good luck or bad luck because, the good news is we had most of our stuff out of there and it was safe in storage. And, yeah, just keep us in your thoughts and prayers. There was so many, it was it was a very hard time, for everyone up here. And, yeah, just keep us in your thoughts and prayers, please. But anyway, let's get started here. So let's go ahead and zoom into our power supply here, and I will explain how all of that works. So, this is where your line cord plugs in. This is where you plug the thing into the wall here, and when you do that, there is 120 volt AC present on this primary. Now, this is the main power switch right here. This guy right here. And so you get 120 volts AC across this, and this is your power switch. So when this is closed, and it's also on the volume control, they made a note for us there that it's the volume knob has a switch on it as well that will close this. Um, and so when this closes, you've got 120 volts across this coil right here, and this is known as the primary of the power transformer. But before we get to that, you may be wondering what these two capacitors are doing right here. Well, those are known as death capacitors. And what they do is they shunt high frequency noise that might be present on the power line. They shunt those to ground because really, if you think about it, the power line is a pretty big antenna. So you want to get rid of those high frequencies to ground. So 60 hertz is a very, very low frequency. It's an audio frequency technically, and um, to 60 hertz that's going to be on this line, these capacitors look like a very high impedance. So, the reactance of a capacitor and, its impedance is really 1 over 2 pi times FC. So as F increases, the reactance will decrease because it's inversely proportional to it. And so to 60 hertz, these kind of look like an open circuit, but to RF frequencies and higher audio frequencies, these start to look like a pretty good path to ground. And you want to shunt those high frequencies to ground so that they don't make it through this power transformer and into the radio. So so they took filtering pretty seriously with this radio, and we'll kind of get into that. So the first thing I want to talk about is the magnetic fields. So this primary will develop a magnetic field that looks something like this, only the blue portion and red portion will constantly be alternating back and forth along with this alternating current that's passing through. And when that happens, what you'll get is well, you notice they have these lines drawn right here. And the schematic designer that they added these to let you know that there is a metal core. There's a ferrite core in this transformer. And when this primary coil is generating an alternating magnetic field, it is actually causing flux to course through this core material, which ends up inducing magnetic fields in these other windings. And the voltage, when you have this magnetic field being induced, there's a voltage that also gets induced on these. And that voltage is proportional to the turns ratio. So looking at the heater filament right here, when you have, it has a certain number of windings compared to this primary that ends up being the same ratio as 120 to 6.3. So this has quite fewer windings than the primary does, and you end up with a lower voltage being induced. Now this winding in the middle right here is your high voltage winding. So that is the B plus winding that it creates the high voltage DC for the tubes to work from. And then this is also another filament winding, but it's individual. It's only for one tube. It's only for this rectifier tube right here. And we'll get to all that. So the 6.3 volt filament winding, what it does is it provides 6.3 volts for the dial lamps. Those light up the dial on the radio, as well as powering all of the heaters in these radios up here. So you notice they've got these little arrows drawn right here. And so every one of these tubes in this radio has a heater on it. They all attach right here in parallel. And they end up getting powered, they glow red hot, and they cause the cathode to start boiling and disassociating electrons from it. All right, so pretty important. So this is one of the old style radios where the filaments are not in series. For a while there in the late 40s, early 50s, there was a new design that came along where they would string these filaments across the 120 volt line. But this one, I really don't like restoring those types of radios. They're, you know, noisy as shit. You have to add some safety precautions to make them a little bit safer. So I definitely prefer like this design a whole lot better. So anyway, you have these magnetic fields here that are inducing voltages that are reliant on the ratio, the turns ratio. So this middle one will actually have a lot more windings than the primary, but they didn't draw it that way. But just know that this one would actually be probably wider than this whole thing if they drew it to scale. But the schematic designer did take care to let you know at least roughly this would be your lowest voltage. So this is rectifiers commonly used 5 volt windings instead of 6.3. And so this would be your 5 volt, which has the least amount of turns. Then this is your middle one. This is your 6.3 volt that has a little bit more. And then this one has the most. So they're kind of tipping their cap to you and letting you know, kind of which one is which. So next we have the filament for the rectifier tube. So this is a 5 volt winding. And there's a little bit of intricacy here that we'll get into, but essentially you've got 5 volts AC that's present on this line, and that is causing this rectifier tube to turn on and work. So this rectifier tube is the only tube in this entire radio that's known as a directly heated vacuum tube. And what that means is that the heater and the cathode are the same thing. They're not separated. So notice up here on these tubes, this would be the cathode for this tube, but it's separate. So this is your heater, and the heater passively heats up the cathode and causes it to boil electrons. This one doesn't have that. The heater and the cathode are the same element within the tube. All right, so let's get rid of this primary magnetic field. There we go. So this is our high voltage B plus winding. This is probably the most interesting one out of all three. So it ties to the plates of this rectifier tube. So these square elements right here are known as plates, and this is usually where your high voltage DC will be applied to the tube. And the cathode normally ties to ground or something. Now it's not here, it doesn't usually with rectifiers, but all of these other tubes up here, it's going to ground through a pretty low value resistor right here. So the current and voltage on this coil right here will look like this. So let's go ahead and put this here, and this is what it will look like half of the time. So half of the time, this voltage on this side of the coil will be negative, and current will be trying to leave this way. And then current will be on this positive line. It will be being pushed out through this plate and ending up on this winding and to the filters for the power supply, for the DC. So notice I drew red on both sides of this coil. And so that brings me to one thing here is that we have grounds on these two coils. There's a ground here and here, but notice there's a conspicuous absence of a ground on this one. And that's for good reason. If you had a ground here, you would have a direct high voltage DC short to ground, so we don't want that. So they didn't ground this coil, and essentially what happens is you do have 5-volt AC here, but there's also going to be high voltage DC on this winding, so you wouldn't want to touch it. That would be a bad day for you. So please don't go touching cathodes of rectifier tubes. It's not really a good idea. So half the time the polarity is going to look like this, and then the other half of the time the polarity is going to look like this, where this side of the coil flips positive, current flows out through this plate now, and really you can think of this rectifier tube as two diodes that are forward biased out of this power supply, out of this B plus winding. So current cannot come this way. Even though I drew an arrow here, there's not going to be any current flowing because this is higher voltage than this. This tube will only conduct if the plate is higher than the cathode in voltage. Now this is negative, so the cathode cannot pass electrons to this plate. It can only accept electrons from this one. And likewise, when it reverts the other way, current's going to be flowing out of this one. This plate's going to look negative compared to the cathode, so no current will flow this way. And so this ends up having the effect. So this B plus winding is high voltage AC, but it ends up having the effect that it will chop, or not only will it chop off the negatives, it will force them positive. So you end up with a humpy voltage here. Now it won't look like that if you measure it in most cases. It will if you take these capacitors out, but that brings me to the next thing. Why do we have these capacitors here? Well, since the voltage and current on this cathode is no longer alternating in its polarity, it is technically DC. But it's changing. It's got humps in it, and you need to remove the humps. So the next thing in line right here is a shunt capacitor. So this capacitor is connecting this high voltage DC into ground, and that creates a low pass filter where these humps will get filtered out and you'll get a nice, relatively clean line. So you want your DC to be nice and stable. You don't want it to be wavering. It would end up showing up in the audio when it's all said and done. Any noise on this line is going to be recreated in the speaker. So you don't want any noise there at all. So this is essentially a low pass or a high pass filter, I'm sorry. So any high frequencies or any changes in voltage will end up getting shunted to ground through here as current, and it's going to keep the voltage relatively stable. All right. So then next in line, so we have a shunt capacitor, then it goes up. Now this is not an intersection right here. This is just passing over this wire, and it comes out into this socket, and it goes across this big coil right here. So this field coil is really an electromagnet for the speaker. So in the old days, they didn't use magnetized speakers, and they relied on this coil to create an electromagnet. So you notice it's drawn with a little tube here that goes up to the cone of the speaker. And so this is actually pretty smart. They were doing double duty here. So not only were they using this to create an electromagnet for the speaker, they were also using it as another high pass filter for the power supply. So with capacitors, they want to resist changes in voltage, and what that means is that they end up having high impedance at low frequencies and low impedance at high frequencies. Well, inductors are the opposite. They create magnetic fields and they resist changes in current. And then, so they have high impedance at high frequencies and low impedance at low frequencies. So this is going to be a low frequency. It's going to be DC. So it's just going to pass through here. This coil is going to create its own magnetic field, but it's not alternating. It's one direction. So it's just going to be magnetized. It's going to magnetize this speaker. And also, any high frequencies that come out of that capacitor, the first one, they're going to try to be blocked here. This coil is going to look like a very high impedance to any high frequency noise. So it's going to get trapped back here. It's going to get trapped back here with this capacitor. And then the DC current will make it through very easily. So this coil is going to look like a dead short to DC. So it comes out of this end, out of this side of the socket, and it goes over here to another capacitor. So this is another shunt capacitor. So you notice we have one shunt capacitor, one series inductor, and another shunt capacitor. So this is really kind of a pi network in the power supply right here. So any additional high frequency noise that happens to make it through here is gonna get shunted to ground right here. And provided that these capacitors are in good shape, they haven't lost too much capacitance, and they're not leaking or anything, you should have a very, very clean DC power supply at this point in the circuit. So notice this, all of these lines that I've traced red right here, these are your high voltage B plus. This is the highest voltage in the radio that you'll have right here. And so it comes out right here, goes all the way this way, and it's doing its job powering. So I want to point out some things while we're here, is that, remember I said that coils look like a dead short to DC? Well, that's why I've drawn this red. In all actuality, this is going to be alternating at the end of the day when this radio kicks on and starts working. But for right now, it's looking like a short to DC. And you have B plus on the plate of this IF tube. And it's also moving through this IF transformer into the plate of the modulator tube. Now, the modulator, that's an old term. It seems like it's came out of fashion. Nowadays, we would call this a mixer tube, but they called it a modulator back in the day. Um, but yeah, it's pretty much a mixer tube. So this is your high voltage DC power supply. This is how the radio is able to work. And yeah, so thank you for watching. I'm going to do a whole series on this, so make sure you tune in and subscribe, like, you know, comment, and yeah. But appreciate y'all. Take care. See you soon.